Hi everyone. In this last lecture video on this topic, we're going to see what are polynomial time reductions or polytime reductions. Okay, so this is going to be a very short video. Uh, what are polynomial time reductions? These are really extending this notion of reductions that we have seen already. So we've looked at mapping reductions and Turing reductions. Okay, and they were very useful in understanding Turing recognizability and decidability, respectively. Okay, so polynomial time reductions are really a special kind of mapping reductions, okay, with an extra constraint, which really enforces an efficiency constraint, and that we'll see in a bit. And this is just very these polynomial time reductions are going to be very useful in understanding efficient computation. Okay, so by efficient computation we mean what can be computed in polynomial time. So this class P that we defined in the previous videos. Okay, so we'll see a lot more about how we can use polynomial time reductions, in the next topic or a couple of topics from now. But in fact, it'll be very useful in also defining this notion of NP completeness, which is an extremely important topic in understanding, what kind of problems are easy and hard. Um, okay, computational problems are easy and hard. Good. So before we go to what polynomial time reductions are, we need to define what is meant by polynomial time or polytime computable functions. Okay, so these are really just functions which take in as input a string, okay, and they produce another string as output. Okay, and this we are going to denote by f of w. And the main thing is that this function should be implementable by a Turing machine which runs in polynomial time. So it's very simple. Okay, so you're already used to this notion of the output of a Turing machine, and here we just want an extra condition that this Turing machine should run in polynomial time. Okay, so that is, it runs in time, order the size of that string raised to the power of k for some k constant k. Okay. Good. So now that we know what polynomial time computable functions are, we'll say that a language so let me actually, okay, good. A language A is polytime or polynomial time reducible to a language B. Okay, so this is denoted by A being uh, polytime reducible to B. So we have a less than or equal to with the subscript P standing for polynomial time. Okay, if and only if there exists a polytime computable function f, okay, such that, okay, so the main condition we want is that if, your string w is an element of the language A, if and only if, okay, f of w is in B. Okay, so this is the same condition that we have seen for a mapping reduction. Okay, so remember this figure. Um, so you have the whole of sigma star you have A, and then you have B, and you want everything which is inside A to get mapped to things inside B. Okay, so this is f of W. And then anything which is outside A to get mapped to things that are outside B. Okay, good. But in addition, you just want this mapping to be polynomial time computable. Good. And we'll also say that F is a polynomial time reduction from A to B. Okay. Good. So it's really just a mapping reduction with this extra constraint of this mapping being polynomial time computable. Okay, good. So note there is, we want this function f to be polynomial time computable. Okay, so one immediate consequence of this is that if you look at the output of the function f, okay, so if you look at the size of the output, so the length of the string output by f, the length of the string cannot be more than a polynomial the size of the original input string. Okay, because f itself takes only polynomial time. So let's say it takes time, um, some n to the k for any input of length k, sorry, any input of length n. Think of k as being 100 or so. Then the output, the output length cannot be more than n to the k, right? Because even writing each of these characters on your tape is going to take 1 unit of computation each. Okay, so the input, so this in particular implies that the output of a reduction is going to be polynomially bounded in terms of the size of the input. Okay, but of course this is not the only condition that's required for a polynomial time reduction. It's just an implication. Okay, so the entire computation needs to be needs to take at most polynomial time. Okay, this in the reduction. Okay. For some key. Good. Okay. So and what do we know? We just to remind you. So W is in A if and only if f of W is in B. So this is a property that we have already seen for mapping reductions. Okay. So now there are, I mean, this notion of a polynomial time reduction is actually very nice because it satisfies the kind of robustness properties that we have already seen in the context of polynomial time computation. Okay, so one, for instance, one nice property that it satisfies is this notion of transitivity. Okay, so here's a simple theorem. If A is polynomial time reducible to B and B is polynomial time reducible to C, then A is polynomial time reducible to C. Okay, so pictorially, we just, I mean, this is actually quite simple to prove. And okay, so let's see what happens. So you have A, you have another language B, okay, and you have another language C. Okay, so this is derivative sigma star. Okay, so we have this. If you take any W, then we know that this mapping. Let's say, I mean, because A is polynomial time reducible to B, you have this mapping F1. Okay, and the output is going to be F1 of W. And what we know is that F1 of W is of size, which is at most, n to the k1 if the length of W is n. Okay, And now we know that, okay, so if w is in A, if and only if f1 of w is going to be in B. Similarly, so if w is not in A, then you will get it mapped to something else here, okay, which is also not in B. Now we also know that B is polynomial time reducible to C, which means that there is another function f2 potentially, okay, which will map these strings in B to some string in C, okay, and similarly strings that are not in B will get mapped to strings that are not in C. Okay, so this is f2, and so for instance this will be um, this will get mapped to some f2 of f1 of w, okay, and the size of the string is going to be at most some f1 of w raised to the power of some k2, where k2 is a constant, okay. But so let me write this out more formally. So good. So why is it why is this transferability hold? Okay, so we know that both f1 and f2 are polynomial time computable. Okay, so let's say that f1 runs in time which is n to the k1 for some constant k1 on inputs of size n. f2 runs in time n to the k2 for inputs of size n. Okay, so now if you, what you're really doing here is to go from a reduction from A to C, we are actually just going to compose the two reductions f1 and f2. Okay, so we're going to compose okay, um, where f1 is the polytime reduction, is a polytime reduction from A to B, and f2 is a polytime reduction from A to C. Sorry, from B to C. Okay. Now, so now if you look at any input W, okay, so suppose, yeah, if you look at any input W, we'll actually show that this composition of the two reductions is only going to take time, which is polynomial in the original input size, that is the length of W. Okay, so why is that? Well, we're going to compose the two reductions. So the string, the intermediate string that we get, so let's say we have W, and then we apply f1 of W, and let's call this some W prime. And then we are going to apply f2 to get f2 of W prime. Okay, which is really actually f2 of f1 of W. Okay, good. Now, what do we know about the length of W prime? Well, the length of W prime is at most, let's say the length of W is n, then the length of W prime is at most some n to the k1, okay, for some constant k1. Good. And we also know that this function f1 is takes time, which is at most n to the k1. Okay. Now, the function f2 on input W prime is going to take time, which is at most W prime's length raised to the power of k2. Okay. But what is the length of W prime? This is at most n to the k1, the whole raised to the power of k2, which is order of n to the k1 times k2. Okay, this is also a polynomial. Okay, just because k1 is a constant, k2 is a constant, so k1 times k2 is a constant. And this is really just saying that, it's just using the fact that that this uh, things are polynomial time. Polynomial time is robust under composition. Okay, polynomial time computability is a very robust notion under this composition. Okay, so this is just a very simple sketch of why transitivity holds. And so now let's see why it's useful. Okay, so um, here is how we will use these polynomial time reductions, just like we used mapping reductions. Okay, so if A is polynomial time reducible to B, and if B is in P, okay, then A is also in P. Okay, so we use mapping reductions to say that if A was mapping reducible to B, and if B is Turing recognizable, then A is also Turing recognizable. Here, if you have the extra condition that is also polynomial time computable, and if B is in P, then A will also be in P. Okay, so it just serves the same purpose in the context of polynomial time computability. Okay, so here's a very simple proof. Okay, so let MB be a polynomial time Turing machine that decides P, and F be a polynomial time reduction from A to B. Okay, so now let's actually design a Turing machine for A. Okay, that decides A, and that runs in polynomial time. So this Turing machine is going to be MA. Okay, so consider MA. So on input W, what are we going to do? We are going to do the obvious thing. We're just going to, design. I mean, we are going to use F to compute this input W prime, which is just going to be F of W. Okay, and W prime is going to be the input to the Turing machine MB. Okay, so we're going to run MB on W prime. And output its answer. Okay, and it's easy to see that firstly, this Turing machine M runs in polynomial time. Okay, because both F and MB are run in polynomial time. Okay, further, W is in A if and only if F of W is in B. Okay, so this is just because of the fact that it's a mapping reduction. Okay, now this completes the proof. Good. Now, just like you can use these polynomial time reductions to talk about to prove that certain languages are in P. You can also use it to prove that languages are in NP. So if A is polynomial time reducible to B and B is in NP, then A is in NP. And the proof is very similar. And finally, you can also use it to prove non-membership. So you can also use it to prove that certain languages are not in P, are not in NP. Okay, and this is just looking at the contrapositive of theorems 2 and 3. Okay, so if A is in B and and A is not in B, then B is not in B. Okay? Similarly, if A is polynomial time reducible to B and A is not in NP, then B is not in NP. Okay, so this is how polynomial time reductions will be very useful in in proving membership or non-membership in P or NP. Okay, and this will be very crucial in the next few lectures to understand or to even define this notion of NP completeness. Okay, thank you.